So we are continuing in 14.2, finding or evaluating limits. So this is what you're actually going to be asked to do. So let's take a look at what it would look like here. So you have the limit of something. So it says something like the limit. Well, let me say it's an example. Okay, so find the limit and something like this. You say the limit of something. So this is x squared minus y squared over x minus y. Then you want to say, and this, you need to fit this in, this is x, y approaches, in this case we'll say 1, 1. It doesn't really matter really what you approach, but any value you put in that's the same on that, in that case, you get 0 over 0. So just like in Calc 1, what you need to do is factor. So, and you got to bring that whole thing along as you go. So this is the limit as, you have to bring the limit along as xy approaches 1, 1. And so just like you would in Calc 1, you factor that numerator. So except you'd have like x, maybe x minus 4 or something, and then you're approaching 2. So, but in our case, you have two different variables. So you treat it the same, or similar, but you have the variables. So this is x plus y, x minus y, all over x minus y. And of course, right there, you can see that the x minus y over x minus y is going to reduce to 1, and you are left with just x plus y. So that's equal to the limit of x plus y as xy approaches 1, 1. And so you get 1 plus 1 when you substitute in is equal to 2. Okay, so similarly, rationalizing an expression, the other, so one of the cases is factoring. Another case is rationalizing. So this is another one. So let's take a look at the limit of x plus y minus 4 over the square root of x plus y minus 2 as xy approaches to 2. Now you can it doesn't matter what point you're approaching. So your xy could approach like 0, 1, negative 2, 3. So whatever the ordered pairs are that's in the domain, you can approach, but these happen to be the same. 0, 0, 2, 2, 1, 1. So here, just like in Calc 1, you'll want to rationalize. So you, in this case, the denominator. So you want to rationalize the denominator by doing root x plus y plus 2 over itself. Root x plus y plus 2, like that. So the numerator, you got to work out. Denominator factor, or the products is what you'd expect. It's a difference of squares. So you're going to be factoring into a difference of squares. That's always how the product works when you do like the conjugate. So we're using that. So when you multiply this out in the numerator, we're going to come back over here. That's the limit xy approaches to 2. And so in the numerator, let's see, we'll just leave it for now. So that's just x plus y minus 4 times square root x plus y plus 2. So I'm not sure if we need to multiply that out or not. I don't think we do. The denominator ends up being x plus y minus 4. Oh, and look, do you see an x plus y minus 4? Yes, we do. So you see an x, here's your x plus y minus 4. Oops, that's too big. Just use that other pen. So here's x plus y minus 4. That gets to reduce. And so you're left with just the x plus y plus 2. And so you can just take the limit right there. You don't have to show the next step, really. So that'll just be 2 plus 2, so it'll be 4. So it ends up being, you can just now substitute in directly. So 2 plus 2 plus 2, so that's root 4 plus 2, so it's equal to 4. Okay, the next case is a special type of case. So far all these are working nicely. That's kind of what happens. This next one is a special case. Now, pretty much only do this if the book or I ask you to do this. It's not a go-to. So I'll show you what I mean. The limit x cubed minus x y squared all over x squared plus y squared as xy approaches 0, 0. So if you try to substitute in 0, 0, you're going to get indeterminate. Right? You still get 0 over 0 as an indeterminate. So, so what we want to do, if it's not obvious or they ask you to do it, so let me put this down in writing for you. What we're going to do is change to polar. So I'm going to write this down. Only change to polar if asked. So the book or I may ask you, but it's really not a go-to method. So that's what this technique is. So we're going to change to polar coordinates. So you basically let x equal r cosine theta and y equal r sine theta. And have, now this only works when you approach 0, 0. And have r approach 0 implies xy approaches 0, 0. So that's your basic technique. So you substitute in for x and y, and then you just have r approach 0. So basically, it's because of this implication. Hold on one second. So it's because of this implication and that, well, that, whatever. Since xy approaches 0, 0 implies r approaches 0. So theta basically just becomes like a dummy variable. It's not going to matter what theta does. Theta is just kind of going around, but you're still approaching 0, 0. Okay, not a very good depiction of what's going on, but you get the idea. So substitute, and you get, you do your substitution, and you get all of this. You get the limit, and now we're going to say just r approaches 0. And it's going to be r cubed cosine cubed theta minus r cosine theta r squared sine squared theta all over r squared cosine squared theta plus r squared sine squared theta. So do you see things that might be able to factor? Right, so the you have basically in the numerator you got r squared and r, so that's r cubed, and you have another r cubed here. And then in the denominator you have an r squared and r squared. So we can, well, that was weird. So we can factor out the r cubed, and we have that this is equal to, oops, can't forget the limit. Gotta put the limit in there. So actually, let's come down here because it gets kind of messy and long. So this is equal to the limit as r approaches 0, r cubed cosine cubed theta minus cosine theta sine squared theta all over r squared. And then that'll just be 1, which is kind of important to have it simplify. Well, actually, it's important that you have r reduce out and simplify. So basically, you get the limit of r times all of that all over 1. And basically, it doesn't matter what that is. So whatever's here, like, who cares? It doesn't matter because it's just theta does not change what the function's approaching, and so you just get 0. Okay, so there's a few like that in the book that you'll be asked to do, or if I ask you to do it. Otherwise, we're using other techniques. Okay, next one. So you can try any of these as you go, obviously, but try this one. The limit of x minus y over x to the 4th minus y to the 4th. As xy approaches 2. Okay, so limit as xy approaches 2. And then so the difficulty in this one is just factoring out x to the 4th. So x to the 4th minus y to the 4th factors to x squared plus y squared, x squared minus y squared, of course all in parentheses, and then that factors to x squared. That's done. No imaginary numbers. And then this will be x plus y, x minus y. So that's what's in the denominator, x squared plus y squared, x plus y, x minus y. And then you can see here that the x minus y will reduce. So you end up with a 1 over that. So that's equal to the limit as x, y approaches 2. So it's 1 over all of that. So you can just substitute in directly. There's nothing to make it indeterminate or undefined or anything. So you get 2 squared, so 8, and then 12? No. Oh, you got to do the product, so you get 32. Okay, so that's equal to 1 over, we'll just write it out. So you get 4 plus 4, and then times 4, so it's 8 times 4 is a 1 over 32. Okay, so those are the easy ones. Well, not easy, but those are the ones where you get a solution, you get a value. So what we want to show next is if the limit exists or not. So this is the case where you might get different, depending on how you're approaching the limit, you might get different values. So this is kind of analogous to something like this. So if you have a function like this, and then, let's see, and then it might jump or something and do something else. So those limits would be different. But now we're looking at, so like a cusp as well. Like if you have a cusp, then that limit doesn't exist. The limit approaches infinity. It could be negative infinity, right? Cusp like that. Okay. Let's see. A corner, actually, on either side. Well, the limit exists, but the derivative wouldn't. But still, in those cases, the limits wouldn't exist. But now you're looking at 3D. So in 3D, what happens? And I'll do this in the second video, but I'll show you what it might look like when you have a function that doesn't exist at a point. So that's what this is more about. So what happens, so in 3D, what happens, actually is a good question. What happens when the limit doesn't exist? So that's a good place to start. So let's just look at that. Okay, so let's take a look at this example. The limit x squared plus y squared, nope, sorry, that's a minus, x squared minus y squared over x squared plus y squared. And we're going to approach 0, 0 as xy approaches 0, 0. So if you factor that isn't going to help. You get x plus y, x minus y, nothing to reduce in the denominator. If you substitute in 0, 0, you get 0 over 0. So there's nothing you can factor or do to figure this out other than is it going to exist or not. And so if you're not sure how to find the limit or can't prove what it is somehow, then maybe the limit doesn't exist. And in many cases, I'll ask that, if a limit doesn't exist or show that a limit doesn't exist. So what you do this concept is you approach the point. So approach the limit point on different paths. So when you're approaching, so as xy approaches your point x naught, y naught, in this case it's 0, 0. So what different paths basically go through 0, 0? Well, the idea is this. If you have a point, and we'll use this one in question here, 0, 0. So you're approaching 0, 0. Here, you can approach in different ways. Like you can basically come in on the x-axis like this, come in on both sides like that. You can approach on the line y equals x like this. So you're coming in like that. So that's be like y equals x. This is y equals 0. Of course, you can approach on vertically, right, on the y-axis like that. In that case, that's x equals 0. But then you can also approach on, I don't know, how about y equals x squared? Come in like this. Okay, so that's y equals x squared. All of those different paths as you're coming in like this basically. Okay, so you're coming in like this. we'll get to 0, 0 at some point. We'll still get to here. And so you essentially set your values equal to these different cases and see if two different paths, say y equals 0 or x equals 0, so coming in like this versus this, give you two different values. Okay, so that's the idea. I'll write it up too in a bit. So what you do then is you let or set, we're going to set, in this case, y equal to 0. And so this is along the x-axis. And what's your limit? So when you do that, you get the limit as xy approaches 0, 0. And you get x squared over y squared is equal to 1. Without even substituting in 0, 0. Oops. I said y squared, I meant x squared. Okay, so when you substitute in 0, 0 here and here, you get x squared over x squared, which is always 1. You don't even do the limit or plug it in, right? So then you approach on a different path. Now you want to pick the easiest case first. So we're going to set x equal to 0 to pick an easy case. So this is along the y-axis, right? So we're going to do that next, and you'll see what limit do you get. So now when you plug it in like that, substitute in, you get negative y squared over y squared, which is negative 1. So those two different paths, 2, 0, 0, give us two different limits. So therefore, since two different paths, 2, 0, 0, give us, or I'll just say yield, two different limits, by, actually has a name, the two-path rule, by it's called the two-path rule. Sorry, I'm getting ahead of myself there. The limit doesn't exist. So DNE. So that's what the two-path rule says. If two different paths to a limit value gives us two different limits, then the limit doesn't exist, which is exactly really what's going on here. Right here, you're getting a limit to here, and this limit from the other side is different. When those are different, we say the limit doesn't exist. Or in this case, you could have a limit. Well, I mean, this could be a corner. Your limit on this side might be a slope of 1, and the limit on this side might be a slope of negative 5. And then so since those limits are different, well, that was slope example. Okay, that was a slope example. So in this case, it would be an infinite limit, which could occur, but we're focused more on the two different actual values. So two-path rule, and so that was a simple case, and then they get a little more complicated on what to approach. So let's try this one. So you try the simple cases first, like 0 and 0, and then if that doesn't work, try something else. So let's look at this one. The limit x squared over y over x to the fourth plus y to the second. And we are again approaching 0, 0. So if you tried x equals 0 and y equals 0, well, you get 0. So that's not going to work. You can't try that case. So what you may want to do is you try y equal to x as one path. Okay, so, and I'll just work it out. So you get the limit. So at this point, I want you to try this. Okay, so try working this one out. And I'll just give you the punchline because it takes some time to think about it. Another one to try is x squared, y equals x squared. So first we'll let y equals x, then we'll let y equals x squared and see what happens. And I'll go ahead and work it out this time. Okay, so after you've looked at it. So we'll first do case 1. We'll let y equals x, so you get x cubed over, and so that'll be x to the 4th plus x squared. Okay, so then you keep evaluating. So it's the limit of xy approaches 0, 0. You factor out x squared, you're left with x squared plus 1. Oops. Numerator is x cubed. And so it looks like you're going to approach 0 because you still get the x squared is gone on the denominator, but you still have a fixed value to be, so it's 1 in the denominator. So you get xy approaching 0, 0. And so this is x over x squared plus 1. So that's going to equal 0 because the denominator isn't 0. And so the whole thing is equal to 0. Okay, and I'm going to move that over because I always do that. Got to start from the left-hand side. So we can use the whole chalkboard. Okay, so next, let's let y equals x squared. So this was case 1. So I'll do case 2. So you get the limit xy approaches 0, 0. Okay, so when you get x squared, y equals x squared. All right, so you get x to the 4th, and then you get x to the 4th plus x to the 4th. Okay, so that's going to be, I'll write out one more step. Limit, what is it? Can you see what that's going to be? That's basically x to the 4th over 2x to the 4th. So that's just 1/2 without even evaluating. And there you have it. You get 0 in one case, 1/2 in the other case. And so when that occurs, you don't have to like restate that they're different. You can read that they're different. Now you draw a conclusion. Now you say, therefore, by the 2-path rule, the limit doesn't exist. But you must say that. So we must say, you can't stop. So we must state the reason. Okay, so let's state the reason. So therefore, by the 2-path rule, the limit does not exist. That's good enough. So there's other cases to do. One way, another one to look at that comes up is you approach on any line through the origin, or if it's not through the origin, you make the line go through a point. You could do mx plus b. And then that line you can make go through any point, and then different values of the slope will give you different limits. So then you can conclude if m equals, something, or m equals something else, you get two different limits. So that's another way to approach 0, 0, and it may not work in this case above. It depends on what the function is. But that's another it's another thing to try. So that incorporates every line that goes through the origin, right? And you just have to pick two of them, right? So you pick if any of those two slopes. So you got to keep in mind too that this only proves, I didn't state this above, so the two path rule only proves D and E. So write that down. Really important. The two path rule only proves D and E. Because one of the ideas is, when you're approaching a point, you're coming in, it has to be true for any delta neighborhood around a point. So when you're coming in on a point, it can't be some random one off to the side that it's different, right? So it has to be every point inside that gives you the same value. Okay, let's define now, last thing in this into this section, continuity. So this is the definition of continuity in multiple variable. We'll do 3D. The definition of continuity. All right, so continuous at a point, and then if that point's continuous, if it's true for every value in a region, then it's continuous in the region, that kind of thing. So here's the definition, and we'll talk about it a little bit. So the same as Calc 1 type stuff. So a function f of x, y is continuous at x naught, y naught if 1, f of x naught, y naught is defined. 2, the limit of x, f of xy, as xy approaches x naught, y naught, exists. And 3, this is the limit value equals the function value. And 3, the limit of f of xy as xy approaches x naught, y naught equals f of x naught, y naught. So in most cases, it's 3 that makes the most difference. I mean, basically, that has to be true. It has to exist. So if you plug in f of x naught, y naught, you get a value, which means it's defined. The limit equals that value. So if it equals that value, it's a real number and it must exist. So the key is that this is basically a number in the reals, and then 1 and 2 are satisfied. So the different cases you might see is something like this. And this is a two-dimensional case. So you have something like that. That's like case 1. You could have something like this. Case 2. And then you could have something like this. So all of those are not continuous. So number 1, so which one of 1, 2, 3, which one fails? So on the first case here, is the function value defined? And so you'd say yes, it's whatever this value is. Does the limit exist? Yes, the limit exists. It's the same point on both sides. Do they equal each other? No, they don't equal each other. So it fails 3. So this one here, I'll say this guy fails 3. So what about 2? The second one, is the function defined? Yes. Does the limit exist? Well, no. the limit does not exist. So this fails 2. Well, and 3. Because they're not the same, but it doesn't exist anyway, so but it's really 2. And then 3, this case, does the limit exist? Yes, it's this, whatever this is. Does the function exist, f of x naught? No, this is not even defined, so this fails 1. So the function value, they're not the same, so that'd be like number 1. So this fails. So let's see, f of x naught, y naught's not even defined here, so this fails 1. Okay, and so if the other thing I mentioned is you have a region, this is always defined on a region, so your x naught, y naught is in that region. And so if a function is continuous, it isn't on an interval anymore, it's on the region in the xy plane. So if it's continuous on the region, then it's continuous for all those points in the region. Okay. I think that's it. We'll move on to derivatives next, partial derivatives in 14.3.